Welcome back. We are discussing the next lecture in power electronics. The topic that we will discuss in this particular lecture will be on the power quality issues. So the introduction for this particular lecture goes like this. First, we will discuss the power quality, what is the definition, and what is the reason for taking this topic for today's lecture. The classification of the power quality issues. So, what are the various issues that are being caused in the power quality? And the major power quality issues are basically the voltage sag and the swell, the harmonics, transients, voltage unbalances, and other several power quality issues which affect the quality of the power, and those we are going to focus on. What are the different standards which are basically used to estimate the quality of the power? We will see. Then the mitigation techniques. What are the different monitoring techniques available to estimate the power quality? Certain case studies we will take, and we will also discuss that what are the future trends in this particular area and the conclusion. So let us start with the definition of power quality. So the power quality is basically referred to the degree to which the voltage, frequency, and the waveform of electrical power supply conform to established specifications. So there are certain specifications that need to be obeyed by the electrical power in terms of its voltage, its frequency, and the shape of the waveform. So those factors, if it is not obeyed properly, then the power quality issues will come. So the key characteristics that defines the power quality are in terms of the voltage magnitude, the stability, the frequency stability, the waveform purity which cause low distortion, phase balances in three-phase systems, and the continuity of the supply. So the question is why the power quality actually matters. It may be causing the economic impact or it may be causing the technical impact. So if we talk about the economic impact for power quality, it will damage the equipment and cause its failure. There will be production downtime, the energy inefficiency will be there, and lot of money will be involved in the maintenance cost. When we talk about the technical impact of this power quality, there will be malfunction of the sensitive equipment. Those are a part of the entire power system and the power electronics. There can be data corruption, reduced equipment lifespan, and the system instability. So this technical impact and the economic impact, if we talk about the industry statistics, the poor quality of the power caused the US industries to have an impact of about $150+ billion annually. So we can see from this economic impact how important it is to estimate the quality of the power and to improve the power by removing those issues. When we talk about the power quality in the modern context, the increasing importance is due to the proliferation of sensitive electronic equipment. So a lot of electrical and electronic equipment nowadays are basically part of the modern power system. And we have the integration of the renewable energy sources. Nowadays, a lot of solar, wind, tidal, etc. are integrated within the power grid, and those are basically responsible for these issues. We have a tremendous growth of electric vehicles and the charging infrastructure, which are causing the power quality issues. There is a development of smart grid, industrial automation, and digitization. So this we talk about the modern context as the development of the various infrastructure, technologies, integration of the different aspects of the power, use of new type of equipments. These all are resulted in the issues caused to the power quality. So the main sectors which are basically affected by the deterioration of the power are the data centers, hospitals, manufacturing sectors, telecommunications, and the financial services. The power quality disturbance, if we want to classify into different categories, so these categories may be transient, short duration of the pulse, long duration, the voltage imbalances, voltage distortion, and the frequency variation. We try to measure these categories in terms of its duration and the magnitude. And generally, the unit that we use is in per unit. And we also estimate how much harmonics are there. So there is total harmonic distortion, generally given by the short form THD. So these categories of transients where duration is less than 0.5 cycles. So we know that frequency is measured in hertz. So if we say 1 hertz, it is equal to 1 cycle per second. So the power supply is basically measured in the frequency, which is in cycles or the hertz. So the transient duration should be less than 0.5 cycles and the magnitude will be high. Short duration and long durations may be in the cycle from 0.5 to 1 minute and magnitude may be 0.1 to 12.8 per unit. Long duration can be greater than 1 minute duration and corresponding its amplitude may be 0.8 to 1.1. Voltage imbalance, we talk about the steady state. It can be in the magnitude of 0.5 to 2%, and the waveform in the steady state can have distortion from 0 to 20% THD. Frequency variation is less than 10 seconds and the magnitude is plus minus 1 hertz. Remember, the frequency is for a country, like for example in India, we have 50 hertz frequency supply and for US, the frequency is 60 hertz. So these frequency variations limited up to plus minus 1 hertz. So they are basically defined to estimate the quality of the power in terms of the voltage magnitude or the waveform or the frequency and so on and so forth. Now let us discuss these issues one by one. So the first one we will discuss about the voltage sag or the voltage dip, and we define it as temporary reduction in the RMS, that is the root mean square voltage magnitude between 0.1 and 0.9 per unit lasting for 0.5 cycle to 1 minute. For AC voltage, we generally measure it in terms of the RMS quantities. So if there is a sag in the voltage, which is known as the dipping of the voltage, and these magnitudes of the magnitude of the voltage, which is 0.1 to 0.9, and the cycles, that is frequency of 0.5 cycle for a duration of 1 minute. If it falls, then it caused voltage sagging. Some of the common causes of this voltage sagging may be because of the system fault, which cause 70 to 80% of the sagging. They may have been involved due to the motor starting, because large induction motors are there in the industries, transformer energization, and heavy load switching. So these are basically some of the common causes of the voltage sag. The affected equipments are basically the contactors and relays dropping out, the variable speed drive stripping, the computer and PLC reset, and the lightning flicker. So the first important issue that is basically caused by the power quality is the voltage sag, which is the voltage dipping. And these are affecting various equipments which are in different centers, whether it is a power system equipment or whether it is a data or communication networks. When we talk about the voltage swell, so it is the reciprocal of sag, and there is an increase in the RMS voltage magnitude above 1.1 per unit, and it will be lasting from 0.5 cycle to 1 minute. Here, the common cause is load reduction and single line to ground fault, the capacitor switching, voltage regulator malfunction. And the affected equipments will have insulation stress and breakdown, electronic component damage, premature equipment aging, and motor overheating. So whether it is a voltage sag or voltage swell, both are dangerous. It affects the equipment, and those are caused by different reasons, because of the faults, or there is a change in the load, or certain change in the equipment conditions. Now we'll discuss the harmonics. So let us see the fundamental of harmonics first. So the definition goes like this. Since the voltage or the current are basically in the form of a sine wave, which are known as sinusoidal wave, it is having a frequency that are integer multiple of the fundamental frequency. As we have discussed that for a particular country, we have a certain frequency, whether it is a 50 Hz for India, 60 Hz for US. These frequency are the fundamental frequency. So if you have the integer multiple, integer means if you can have n equal to 1, 2, 3 and so on, the multiple of the fundamental frequencies will be there in our AC supply, and those are basically known as the harmonics. So if we say the current, which is a function of time t, is written in the fundamental component of I1 and sine of omega t plus phi 1. So here omega, if we see, this is equal to 2 pi f1. So where f1 is basically the fundamental frequency, and if we have the harmonics present, then those are basically destroying or hampering the fundamental component of the current or the voltage wave. So the harmonics can be present as the integer multiple. Here we are denoting it with H, which is the harmonic order, and the H harmonic amplitude will be equal to IH. So this is the amplitude of the current due to the presence of harmonics, where I1 is basically the fundamental component of the current amplitude. So the harmonics order, if we talk about that, it can have odd harmonics, even harmonics. Odd harmonics means 3rd, 5th, 7th, 11th and 13th, so on. Whereas even harmonics generally small in the balanced system. So we know that system will be balanced. What is a balanced system? Balanced system is basically where the voltage in each of the phases, VA, VB and VC, these voltage are having equal magnitude with 120-degree phase difference, as well as the impedances in each phases are equal. Then it is a balanced system. The system, if it is a balanced, then the harmonics will be generally small and even harmonics may have been present. Triplen harmonics are 3rd, 9th and 15th, which are the zero sequence component. Zero sequence means the magnitude and the angle are same when we talk about the different phases A, B and C. We can have the positive sequence component or the negative sequence component and the zero sequence component. If we talk about the sources of these harmonics, they may be due to the non-linear nature of the load or the different power electronic devices that are present in the system. Non-linear nature of the load, let us discuss what are those. It is basically means if you can have switch mode power supply, variable frequency drives, the rectifiers or the converters, electronic ballast, arc furnaces and the welding equipment. So these are basically the non-linear nature of the load. If your load is non-linear, the current will also be impacted, because if the load is linear, the current will increase linearly with respect to voltage. If there is non-linear node, then the current will be impacted and the harmonics will be present. Power electronic devices, all these devices we will be discussing in very detail in the advanced lecture of power electronics. We talk about the inverters, UPS system, the battery chargers, LED drivers, solar inverters, electric vehicle chargers. So these equipments generally are having the inductor and the capacitor as a part of the device, which result in the harmonics, that is the nth order of the fundamental frequency. So the key point that you need to remember is that the modern electronic equipment is both a source and victim of harmonics. So whatever the electronic equipment we are generally using nowadays, they are producing the harmonics. So it is a source. It is also being affected by the harmonics which are formed or present because of the other systems. Now, these harmonics are basically measured in terms of the THD, which is the total harmonic distortion. It can be in the voltage wave or it can be in the current wave. So if we measure the THD for the voltage wave, we are basically taking the reference as the fundamental component. So V1 and I1 are the fundamental component of the voltage and the current. And in the numerator, we have the component of the harmonics all present from 2 to infinity and summation of that to the square of that component. So we are basically measuring it in terms of the percentage. So it have the multiplied with 100%. The IEEE 519 limit this voltage and the current harmonics to be less than 5% at PCC, and it varies with the ratio of the current which is short circuit by the load current ratio. Individual harmonics can be less than 3% of the fundamental. So these limits are basically specified by the IEEE standard 519, and the equipments or the system need to be obeyed to reduce the harmonic component. What are the effects of harmonics on the electrical equipments? So we can have the transformer overheating because the K factor rating is needed. K factor is again the transformer turns ratio factor. The modern torque, pulsation and heating will be there. If we talk about the cable heating due to the skin effect, the capacitor overloading, impedance is directly proportional to the inverse of the frequency. So the capacitor overloading will be there. Neutral conductor overloading because of these tripling harmonics. So these are impacting the individual electrical equipment. And if we talk about the entire power system in general, then there will be increased losses and the efficiency will be reduced. A resonance condition will be created. Interference will be there with the communication system, and the protective relay misoperation can be there. So the harmonics have different negative impact on individual equipment as well as on the entire power system. When we talk about the classification of the transients, so transients are very short duration, which are the impulse, and they can be current impulse or voltage impulse. So this impulsive transient are generally unidirectional in terms of the polarity, and they have a duration from nanosecond to millisecond. So this is very fast. The reasons are basically due to lighting or the switching operation, which cause the peak values of the voltage of the current wave to reach several thousand volts or ampere. The oscillatory transients are bidirectional in polarity. They can have a frequency of 5 kilohertz to 5 megahertz. It can cause because of capacitor bank switching or cable switching, and duration may be 0.3 to 50 millisecond. So bidirectional means both positive and negative transient waves are there. So the protection equipment like surge protective devices or proper grounding is required for this transient to be controlled. Voltage unbalance may also occur. This is the ratio of negative or zero sequence voltage component to positive sequence component. So we are measuring this voltage unbalance as the ratio of the voltage of the negative sequence component to voltage of the positive sequence component into 100 to convert it into percentage. The causes may be due to single phase load on a three phase system, unequal line impedances which cause unbalancing, open delta transformer connections, blown fuses in three phase equipment. So these are some of the causes which causes the voltage unbalance. It can affect on the motor. For example, if there is a 2% voltage unbalancing, then it can cause 18% current unbalance. It will reduce the efficiency and increase the heating in the equipment. Torque pulsation will be there at twice the line frequency. So if there is a change in the voltage, then it will be correspondingly causing multiple effects on the system in terms of its current, heating, efficiency, losses, and pulsation. Voltage flicker. This is another issue of power quality. It is basically the cyclic variation in voltage envelope causing visible light intensity changes. So we are basically seeing certain light whose intensity is changing due to the variation of the voltage envelope in the cyclic nature. These are measurement in terms of the short term PST and the long term, which is the PLT flicker indices. So these are the indices which are basically used to measure the flickering in the voltage. Some of the common sources are basically in the arc furnaces, which is the steel industry, the welding equipment, wind turbines, and the motor starting. So in the wind turbines and the motor starting, welding equipment and the furnaces, these are where we can see the voltage flickering. Human perception, if we talk about, the most sensitive to flicker at 8.8 Hz frequency. So in terms of the humans we are talking about, because we are the one who can see this flickering, so they are basically sensitive when this flickering is taking place at a frequency of 8.8 Hz. There is variation in the frequency and interruption. So normally the frequency variation can have from 0 plus minus 0.1 Hz, and they cause the generation or load imbalance, and the effect is in the motor speed changes or timing error. Power interruptions can be there momentary from 0.5 cycle to 3 second, and temporary if we talk about then 3 second to 1 minute, and sustained if we talk about then greater than 1 minute. So there can be power interruptions due to the frequency variations, which can be for a small duration or a large duration. The reliability indices that we used, one is the SAFI, which is System Average Interruption Frequency Index. Second one is SIDI, which is System Average Interruption Duration Index. So one is measured in terms of the frequency and other is measured in terms of the duration. So these two reliability indices are basically used to measure the frequency variation. If we talk about the certain standard internationally, so there are different IEEE, IEC, EN or IEC standard which measure the different issues of the power, whether in terms of harmonic, measurement method, supply voltage characteristic, monitoring practice, flicker measurement, surge environment. So certain key limits they have set in terms of the harmonic distortion less than 5%, class A and B requirement will be there for the measurement, plus minus 10% voltage variation can be there in the supply voltage, even categorization in monitoring practice, PST data can be less than 1, and location categories for the surge environment. So when we talk about the power quality or the power quality issues for different reasons, different standards need to be followed, and these standard, whatever the limits they have specified, that need to be followed. The CBEMA or ITIC curve, it defines the acceptable voltage versus time envelope for the sensitive equipment. So those equipment which are very sensitive to the change in the voltage, frequency or the waveform, we need to obtain their acceptable voltage versus time limit through a curve which are given by this standard. The mitigation strategy overview, if we talk about like how we can deal with these issues of power quality in terms of the passive solution or the active solution. So the passive solution can have the LC filters, K-rated transformers, phase shifting transformer, isolation transformer and surge resistors. Active solution can have the active power filter, dynamic voltage restorers, static VR compensators, the UPS system, power conditioners. So different solutions or mitigation techniques are there, whether it is active or the passive, and the selection criteria depends upon the cost, effectiveness, maintenance, space requirement and the response time. So we can choose these solutions depending upon our criteria, which are given in terms of different parameters, whether it is costing, effectiveness, and so on and so forth. Harmonic mitigation can be done in terms of passive filters, active filters, or design consideration. Passive filters are tuned to specific harmonic frequencies. They are simple and cost-effective and may create resonance issues, whereas active filters will inject compensating current. They are adaptive and flexible, higher cost, but provide better performance. Design consideration, we can have the dominant harmonic order to be taken into consideration, the system impedance characteristic, future load growth, and cost benefit analysis. So whenever power system is basically designed, so from the design point of view, we need to know these conditions, like what are the dominant harmonic order that can have in the system, what can be the future conditions in terms of the load growth, or what can be the impedance characteristic, and what are the cost benefit by designing and taking a proper mitigation measure. Voltage regulation solutions in terms of sagging or swelling, we can have dynamic voltage restorer, which is known as DVR. It can have 0.5 to 30 cycle control. UPS can be there, which is uninterruptible power supply. This provide a complete protection. Voltage regulators can be there, which are tap changing transformers, and STATCOM, which is static synchronous compensators. The selection guidelines depend upon the load criticality and sensitivity, duration and magnitude of the disturbance, available space and budget, and the maintenance requirement. Monitoring requirements to monitor the certain key parameters in terms of the RMS voltage and the current, harmonic spectrum, flicker measurement, frequency variation, power factor and reactive power, unbalanced factors. So these are certain key parameters that we need to monitor. And the monitoring locations is also important in terms of point of common coupling, which is PCC, critical load feeders, before and after mitigation equipment, and utility interconnection points. So what are the parameters that need to monitor and where it has to be monitored? These both are important in power quality. Modern monitoring techniques, if we talk about, then advanced features have come in terms of real-time data logging, remote monitoring via the IoT devices, predictive analytics, automated reporting, integration with SCADA. Data analysis also we do to find the trend, event correlation, statistical reporting, and compliance verification. Some of the benefits that we have is basically early problem detection, optimized maintenance, regulatory compliance, and energy efficiency. So certain benefits are always there when we monitor using the modern techniques for these power quality and we do data analysis. We will take 3 case studies to understand why these power quality issues matter, and if we take proper step, what are the benefit. So let us take the case study 1 in manufacturing plant. The problem is high harmonic distortion is affecting the production equipment. Let us do the analysis. The THD of the current is 28%, whereas IEEE 519 limit to be 8%. So it is quite high if you can see. The dominant harmonics that are present in this production equipment is basically the 5th harmonic, the 7th and the 11th harmonic. So these are the odd harmonics. And the source that are causing this harmonic are multiple variable frequency drives and the rectifiers. So these are the analysis being done by the engineers for this production component, and you have the high harmonic. So what are the solution then we can have? Solution can be the 12 pulse rectifier for large drives, active harmonic filters for the remaining load, and the K13 rated transformer can be utilized. So if we take this solution step, what will be the result then? The THD, which was 28%, now will be reduced to 4.2%. 15% reduction will be there in the energy cost, and it will eliminate the equipment failure. So it means from the case study, what we can have the conclusion is that if you have the harmonics which are present in the system due to multiple reasons and due to multiple causes, we have to do the analysis and we have to take the proper step. If you take the proper step, obviously there will be multiple benefits in terms of the equipment failure reduction as well as the cost. Let us take the second case study in the data center. So problem is the voltage sag is causing the server shutdown. Let us do the analysis. So the analysis says that 50 to 20 sag is there in the event per month. 70% due to utility system fault and critical IT load unable to ride through. So these voltage sag which is there in the data center is causing the server shutdown, and the prior analysis has done. So the conditions have been obtained. What are the conditions over which this problem has been arised, and the solution that is being given is double conversion UPS system should be incorporated, dynamic voltage restorer should be there at the main feeder, and improved ride through capabilities should be incorporated. That will result in zero unplanned downtime, 99.99% availability will be achieved, and substantial cost saving will be there from the avoided outage. So the second case study, which we talk about the voltage sag in the data center, here also we come to a conclusion that if we do the proper analysis and take the proper step, obviously we get the proper results. Third case study we will take, this is final one, which is in the renewable energy integration system. If we take the challenge, the solar farm is causing the voltage fluctuations. And the issues that had been identified are voltage rise is there due to peak generation. There are flickers due to cloud transients, and harmonic injections are there from the inverters that are present in the solar farm. So the solutions that have been implemented to deal with these conditions are smart inverters with proper volt var control, energy storage system for smoothing, and advanced harmonic filtering is implemented. What are the outcomes? Stable grid integration, we got it, improved power quality and enhanced system reliability. So we have taken three important cases to identify, yes, the proper measures need to be taken that will surely give us a positive impact output in the power quality issues. Now we will discuss the emerging challenges. What are the emerging challenges in these power quality issues? The grid modernization. We have the increased renewable penetrations. With the ever increasing demand of electric power, the dependency on the non-renewable energy sources has to be reduced. We are moving towards the renewable energy, and due to this increased renewable penetration, a lot of issues are being come. Electric vehicle charging infrastructure is present from place to place, because now we are moving from diesel to electric vehicle, and these electric vehicle infrastructure are also causing power quality issues. Distributed energy resources are there, microgrid and islanding techniques are also causing the various issues in the grid modernizations. So these are the modernizations that we are taking into consideration, and these are also causing the issues. Some of the technological evaluations that are being taken in the modern era is wide bandgap semiconductors, whether in terms of silicon carbide or gallium nitride we are using, advanced power electronic devices we are using, smart grid integration we are doing, artificial intelligence we are incorporating in the power system. So these are the technological evaluation. And the key challenge is maintaining the power quality while transitioning to sustainable energy system. We are basically modernizing our grid as well as modernizing the different equipment which are causing the various reasons for this power quality. Hence, we need to maintain a proper power quality so that sustainable energy can be provided. Advanced solution for the next generation technologies, because of the grid forming inverters, virtual power plants, machine learning for predictive maintenance, and blockchain for energy transactions. So these are the next generation technologies. Certain standard evaluations are there in terms of IEEE and IAC standards in the smart grid and the communication protocol, updated harmonic standards and cyber security requirement. So standards are also basically evolved. And let us take what are the key takeaways from these discussions that we have done for the power quality. Is basically the power quality is critical for the modern electrical system and the digital economy. There can be multiple disturbance types, require different mitigation approaches. Standard compliance ensures interoperability and system reliability. Monitoring and analysis are essential to effective power quality management, and technology advancement offer new solutions but also create new challenges. So we have seen that with the modernization of electric power system and the equipment, there are different causes of the issues which are arising in the power quality. These need to be monitored, analyzed, and certain standards need to be maintained so that we get the proper power. Design philosophy, if we talk about, then prevention is better than cure, we say. Consider power quality from the design stage. So right from the design stage, if we consider the power quality as one of the important parameters to be considered, then these will be taken into consideration and the issues will be brought down tremendously. Some of the practical recommendations from the engineers: understand the load characteristic and sensitivities, select appropriate equipment ratings, implement monitoring at critical points, and consider life cycle cost in solution selection. When we talk about the system operators, they should establish clear power quality objectives, develop mitigation strategies, maintain updated standard compliance, and invest in operator training. So these are certain steps that need to be taken by the engineers or the system operators so that the power quality can be have certain check. Apart from this discussion, which was the introductory discussion on the power quality issues, where we have not gone into very deep on the different techniques, we have just introduced the different reasons for the power quality, what are their monitoring techniques, and how different methodologies or strategies can be adopted to control this power quality. Some of the topics that we can further explore is basically in terms of the mitigation design and calculations, economic analysis of the power quality solutions, integration with the renewable energy systems, and advanced monitoring and control strategies. So this power quality is a very big topic, and we had just taken into the very introductory introductory lecture, where we have introduced you about the different reasons for this power quality and what are their impact, and how we can have the control. Thank you for now. See you in the next lecture.